I think last time we were discussing about moment area method. Okay, first of all I want to make a correction in the last lecture when we were discussing moment area method. I told you that you have to use bending moment diagram. Okay, so please correct that it is not bending moment diagram, it is M by EI diagram. Okay, M by EI diagram. I think in the last lecture I told you to draw BMD, but that is wrong. You have to actually draw bending moment diagram. Okay, so I think in this lecture we will try to solve a couple of questions related to bending moment area method. And before we proceed, let me just brush up what is moment area method. Suppose you have a beam like this. Okay, you have a pin joint here, a roller here, and some loading you are having. Okay, the first thing that you have to do or the thing that you have to find out is, suppose you need to find out some deflection and some rotation. That is the objective of moment area method, to find out deflection and rotation at any point in your beam. Now the first thing that you will do is you will draw the M by EI diagram. Okay, M by EI diagram you have to draw. So suppose you draw the M by EI diagram, so maybe it will come something like this. Okay, something like this. This will be your M by EI diagram. Okay, now I told you the moment area method will use two equations, basically your theta. Suppose you have 2 points here, this is your A and this is your B. Okay, so your theta B minus theta A is area under M by EI diagram. Okay, M by EI diagram between points A and B. Okay, I also told you the meaning of this TB upon A. This means that suppose the deflected shape is like this. Okay, and you have one point A here, somewhere here, and one point B here. Now suppose you draw a tangent at A, something like this. Okay, so if you draw a tangent at A, this distance, okay, this black distance that I am showing is TB upon A, and the value of this is given by, suppose this is your M by EI diagram. Okay, you have moment of area under M by EI diagram between points A and B about point B. Okay, which means that whatever area you are getting between A and B, and suppose the CG of area is lying somewhere here, so this distance is suppose X, so this area multiplied by X will give you moment of this area, and that is nothing but TB upon A. These are the basics that I think we have covered in the last class. I have just brushed it up for you. Now let's start with a couple of questions. Okay, I think last time we didn't solve any question, so this time we'll focus on questions. Okay, let's start with a simple problem. Suppose you have one beam here which is containing of this type of sections. Okay, the inertia of this section is 2I, the inertia of this section is I, this part is fixed, and you are applied with an external moment of 500 kilonewton meter. Okay, this length is given to be as 4 meters and this length is given to be as 3 meters. Okay, Young's modulus is given to be as E. What you have to do is you have to find, okay, this is suppose point B and this end is suppose point A. You have to find deflection at B and deflection at A. Okay, use moment area method, of course. Okay, use moment area method. Now before you proceed with this question, okay, I appreciate if you draw the deflected shape of this beam. Okay, draw the deflected shape of this beam. Obviously your loading is, see, your moment is trying to twist this section upward. Okay, so what will be the deflected shape like? Okay, your deflected shape will be something like this, isn't it? Something like this. Somewhere here you will have your point B and somewhere here you will have your point A. Now think about it. We have defined this quantity called TB by A. Okay, in this case, suppose I am naming this joint as C, supports point. Okay, so if I draw a tangent at C, okay, tangent at C will be something like this. So this value that I am showing with red, this value is nothing but TB upon C. okay, and this value is nothing but TA upon C. Is it clear? And fortunately this is nothing but your delta B, and TA by C is nothing but your delta F. That is what we have to find out. Okay, let's start. Okay, the first step that is there is you have to draw the M by EI diagram. Okay, M by EI diagram you have to draw. So look here, I am drawing the M by EI diagram. Okay, shear force is not required, just M by EI diagram is there. First tell me what is the reaction here. Will we get any lateral reaction? No, because there is no vertical loading on the beam, so you won't get any reaction here. You will only get one moment, okay, here equal to 500. Is it okay? Equal to 500. Now, okay, now in all the section there is constant moment of M, 500. Okay, so just what you have to do in this section, you will be having M by EI as M by 2 EI. Okay, like this. Okay, and from here you will be having M by EI. Okay, I think you are able to understand. Your bending moment M by EI diagram will look something like this. This is not the bending moment diagram, it is M by EI diagram. Okay, so this value here is 500 upon 2 EI, because the inertia is 2I here, be careful. Okay, and here your value is 500 upon EI, because inertia is I in this beam. Okay, moment diagram will be constant, it is constant moment 500, but when you divide it by EI, this value will be less in this half, and this value will be more in this half. Okay, obviously it is positive, no need to indicate it. Now let's calculate TB upon C. Okay, TB upon C is fortunately nothing but delta B, as I have shown from the deflected shape. Okay, so TB upon C is equal to how much? Area, this is your C point here, this is your B point here, and this is your A point here. Okay, so the area that you are having, I am shading with blue. Okay, the area between B and C multiplied with, okay, multiply with the distance of CG of this area from point B, which is nothing but, say this is 0, this is your 4, and this is your 7, so this is 4, so this will be equal to 2. Okay, so what is the area of this rectangle? 500 upon 2 EI, okay, multiplied by distance, that is 4. Okay, this length is nothing but 4. Okay, multiplied with the distance from CG, this is your CG, the blue dot that I have shown. Okay, from B point, what is the distance of this CG? It is 2 meters, so multiply by 2. Okay, if you solve it, I think you will get 2000 upon EI, and it is also equal to your delta B. Okay, very simple question, I think you are able to understand. Now come here. Okay, here you have to be a little careful. I want to calculate TA by C, which is fortunately equal to delta C. Look here, oh, delta A, sorry, delta A. Now TA by C, TA by C means area between point A and point C, which is this entire area. Okay, multiply by, okay, multiply with distance of CG from point A. Okay, so what I am doing, rather than creating an equivalent CG, I am separately doing it for this blue area and this red area. Okay, first I am solving for red area. Okay, so your TA by C is equal to TA by C is equal to, for the red area, okay, this is your red area. So red area, what is the area? It is 500 upon EI, multiply with this distance is 3, so it is 3, multiply with distance from the CG from A, it is nothing but 3 by 2. Okay, plus, now I am solving for this blue area. Okay, so the area is 500 upon 2 EI into 4. Now be careful, don't multiply with 2, because we want distance from point A. Okay, distance of this CG from point A, what is the value? 3 plus 2, that is 5. Okay, so don't make this mistake here, it should be 5. What is the value that you will get here? Okay, I think you will get 7. Just check it, I'm not sure. Let me just check. This is 2, so this 5000. Okay, this will be 5000 upon EI, and this will be 250. Okay, 250 into 9. So I think 2250. So okay, 7250 you will get. Okay, 7250 upon EI. It is correct. 7250 upon EI. This is your deflection at A point. Okay, so this type of question can be asked where your inertia is varying Okay, so I think it is very simple, you can solve it. Moving to the second problem, let's solve a simply supported beam. Because cantilever is very simple to solve, there is some problem in solving for simply supported beam. Suppose you have a simply supported beam, you have a load of 20 kilonewton here. Okay, there is some point C here located at 3 meters, this is also 3 meter, and this rest is 6 meters, so it is acting at the center. Okay, first thing that you can do is draw the deflected shape. So you know the deflected shape will be something like this. Somewhere here you are having C. Okay, the question that is there is you have to find delta C. EI is constant throughout the span. EI is constant throughout the span. You have to find delta C using moment area. Now this delta C I have to find out. Suppose I am naming this point A and this point as B. I think I have told you how to find out these type of questions. What you do, you draw a tangent at A. Okay, once you draw a tangent at A, this distance from point B is nothing but TB upon A. This length is suppose L. So can you find the value of this theta A? Apply tan theta here. Tan theta will be how much? TB upon A divided by L. Okay, TB upon A divided by L. Apply tan theta in this triangle that has been created. Okay, once you have theta A, can you tell me this value? Let me use another color. Black, green. Okay, this value from C point to the tangent. Suppose I am calling it XC. Can you give me the value XC? Okay, use tan theta in this smaller triangle. What will you get? Theta A is equal to XC divided by this distance is nothing but 3 meters. Okay, so XC by 3. So XC is equal to 3 into theta C. Can I say this? Okay, now one more thing you can say. This small red distance, this small red that I have shown, this is nothing but TC by A. Okay, now can I find out delta C? Okay, delta C is how much? It is XC minus TC upon A. Okay, so all you have to do is find out XC, which is also being calculated. It is 3 times of theta C. Okay, theta A, theta A. Okay, and TC upon A you can calculate. Okay, so I think groundwork has been done. Now all you have to do is draw the bending moment or M by A diagram. Okay, M by A diagram you can draw. I think EI is constant, so it will look very similar to your simple bending moment diagram. The only difference is this will be how much? It is normally PL by 4, isn't it? So 20 into 12 by 4, so you will get 60 upon EI. Okay, so this is your M by EI curve. Okay, this is 0, 6, 12. Somewhere here your C point is lying. Okay, so I am just marking it C. Is it okay? Let's find out. First let's find out theta A. Theta A is nothing but TBA by L. Okay, TBA, how will I calculate? TBA is nothing, this is your point A, this is your point B, this entire area, okay, multiplied by, somewhere here you will have your CG of triangle. Okay, so multiply this with the CG distance. So what you will get? What you will get? I think you will get, okay, so TB by is equal to area. What is the area of triangle? Half into, this is 12, okay, this whole length is 12, multiplied by 60 upon EI, multiplied with distance, this is your 6. Okay, so what will you get? TB upon A. I think if you cancel this, I think you will get 2160 upon EI. Okay, just check the calculation, there may be calculation mistake. Okay, now you can calculate your theta A. It is nothing but TB B by A upon L, that is 2160 upon EI divided by 12. Okay, so theta A will come out to be 180 upon EI. 180 upon EI. Now since I have theta A, can I calculate XC? See here at the top, XC is nothing but 3 times of theta A. So 3 into 180 upon EI, I think you will get 540 upon EI. Is it okay? XC also now you have. Now the only thing that you want to calculate is TC upon A and your job is done. Okay, so TC upon A means this small triangle, the black triangle that I have shown you here. Okay, so what is the area of this triangle? Half into 3 into, what is this value, this blue value? Okay, is it half of 60 by 3i, that is 30 upon ei, isn't it? Because it is at 6 meters you have this value, so what is the value at 3 meters? Okay, it's a simple problem, so you will get 30 upon ei. So half into 3 into 30 upon ei, this is your area, multiplied by distance of CG of this triangle. I think it is 1/3 of 3, that is 1. Okay, so the value that you will get here is, I think, 45 upon ei. Okay, now I think our job is done. Delta C is equal to nothing but XC minus TC upon A, that is equal to 540 upon ei minus 45 upon ei. I think you will get 495 upon ei. This is your answer. This is the value of delta C. Okay, I think this was another simple question. Moving on to the third problem that we are having. Okay, the problem is about maximum deflection. Okay, I have already hinted you in the last lecture how will you solve the problem of maximum deflection. Okay, so let's have a problem on maximum deflection. You have something like this. You have a beam here, pin joint here, a roller here. Instead of acting at the center, load is acting somewhere here. The load is P. Okay, this value is L by 4 and this remaining value is 3L by 4. Okay, deflected shape, if I want to draw deflected shape, okay, it will look something like this. Okay, now many people make a mistake here. People presume that your maximum deflection will occur below the loading point. Okay, but make sure that it is not true. In this case, your maximum deflection will not occur at the loading point. It will occur somewhere here. I don't know where it will occur. I am just calling it X. Okay, this is your maximum deflection. Now maximum deflection has a very specific property that the slope at maximum deflection is equal to 0. Okay, a slope is equal to 0 at point of maximum deflection. This property can be used to evaluate where you will get maximum deflection. Okay, it is definitely not under the point of loading. Okay, remember that. Okay, so let's start and draw the bending moment diagram. I think bending moment diagram is very straightforward. Okay, it is something like this. Okay, it will be something like this, isn't it? Something like this. Okay, how much is this reaction? P into 3L by 4 divided by L. So I think it is 3P by 4 and this is P by 4. So what is the moment that you will get? I think you will get 3P L upon 16, and EI is also there because it is M by EI diagram. Okay, so EI is also there. So this is 0, this is L by 4 and this is your L. Okay, now suppose this point I am calling as A, this point as B, and C is the point of maximum deflection. Okay, and D is where your loading is acting. Is it okay? So this point is, let me use another color. This point is A. Okay, this point is D, this point is C, and this point is B. Okay, just to be clear. Now okay, this property is there, slope is equal to 0. I want to make use of this property and find out what is the location of your maximum deflection. Okay, whenever slope comes to your mind, moment area has a very specific property. You can definitely say that your theta C minus theta A is equal to area under M by EI diagram, okay, between points A and C. Okay, A is this one, C is this one, so I am darkening it by this. Okay, or rather I am making a change here. Okay, rather than calling this X, okay, you call X from here, it will be easier. Okay, same thing. Okay, you can take X from either sides, so I am saying X is from this side. Okay, it will be a little easier for us. Okay, this property, this is the basis of solving this question. Okay, because in this case I know that this value is equal to 0. Okay, this value is equal to 0, so theta A I can calculate, and this value I can get as a function of X. Okay, as a function of X I can solve this equation and get the value of X. this is the groundwork or the basis on which we are solving this problem. So let's solve this problem one by one. What you will get. Okay. Okay. Now, theta A I have to calculate. Okay, theta A I have to calculate. What will I do? The same thing that I have done before also. Let me draw the deflected shape again. Okay, your deflected shape is something like this. Okay, this is your A, and suppose what is the point here? B. Okay, so what you do here is the same thing that we did in the last question. Okay, you draw a tangent at A. What will be this value? This is nothing but TB upon A. This is L. Okay, can you give me the value of theta A? Okay, theta A is equal to TB by A divided by L. Now we need the value of TB upon A. TB upon A is nothing but this entire area and its moment about point B. Okay. So what I'm doing is I am breaking this entire moment diagram into two triangles. Okay, one triangle is this one, this green triangle that I'm showing, and the other one is the smaller triangle. Okay, so the first triangle I am taking, the area of this first triangle is how much? Half. Okay, half into 3L by 4 into 3PL upon 16EI. Is it okay? Multiply with 2/3 of this length, so 2/3 of 3L by 4 plus smaller triangle, half L by 4 into, okay, 3PL upon 16EI. Is it okay? Multiply with, it is 1/3 of L by 4 plus 3L by 4. Is it okay? I think you are able to understand this. It is nothing but this area, this green area, multiply with the CG from point B. Okay, similarly this area, small triangle area, and multiply the distance with this point C. Okay, I think you are able to understand this. Okay, if you solve it, you will get it as I think what I am getting. Please check, there may be a calculation mistake. Okay, but whatever we are doing is correct. There may be a calculation mistake. Okay, that is it. 3PL square upon 128 EI. Okay, that is equal to your theta A. Theta A. Okay, now I want to use this equation theta A, this equation here. Okay, this equation is equal to theta A is equal to area under M by EI diagram. Okay, so theta A is equal to area under M by EI diagram between points, this point C and this point A. Can you tell me what is this value? Let me use another color, it is not visible. This value that I am doing with red. Okay, this value is nothing but, suppose this is 3PL upon 16, so this will be equal to how much? 3P upon 16 EI divided by 3L by 4 multiplied with X. Is it okay? Is this thing okay? You know this value. Okay, you know this value, and it is at a distance of how much? 3L by 4. So can you tell me this value which is at a distance of X? Okay, simple question. So this is 3PL upon 16 EI divided by 3L by 4. Okay, so I think you will get P, okay, P upon 4 EI into X. Is there an L also there? X upon L. ठीक है, सही है. Px upon 4EI you will get. Okay, so now the area under the curve is how much? This small triangle and this trapezium. You have a trapezium and you have a small triangle. So area of triangle is how much? Half L by 4 into 3PL upon 16 EI. Okay, this is the area of small triangle plus the area of trapezium is how much? Half 3PL upon 16 EI plus how much? Px upon 4 EI. Okay, Px upon 4 EI multiplied with the distance, that is your 3L by 4 minus X. 3L by 4 minus X, which is equal to theta we have already calculated, is equal to how much? 7PL square by 128 EI. You equate this, the only unknown in this equation is X. Okay, to get the value of X, I have already done it. It will come out to be 0.67 L. Okay, 0.67 L. It will come out to be Once you know the location of your maximum deflection, you can calculate the value of maximum deflection. I am leaving it to you. Okay, just use the bending M by EI diagram and get the value of del max. Okay, once the location is known, you will not have any problem. Okay. Maybe we can solve one more question. आई थिंक मोमेंट एरिया समझ में आ गया होगा. तो हम लोग अब एक इसका दूसरा पार्ट होता है, उसको कहते हैं मोमेंट एरिया बाय पार्ट्स. ओके, बाय पार्ट्स. ये हम तब यूज़ करते हैं जब बेंडिंग मोमेंट डायग्राम बनाना डिफ़िकल्ट हो जाता है. ओके, पॉइंट लोड है, यूडीएल है, इनका बेंडिंग मोमेंट डायग्राम बनाना आसान है. पर जब बेंडिंग मोमेंट डायग्राम बनाना डिफ़िकल्ट हो जाएगा तब हम मोमेंट एरिया बाय पार्ट्स सॉल्व करते हैं. अब बाय पार्ट्स हम कैसे सॉल्व करते हैं समझो. इसमें हम क्या करेंगे, assume one point or rather one support, okay, as fixed. Okay, so assume one support as fixed and draw bending moment diagram of forces individually. Okay, this is the concept that we will follow, okay, for these types of questions. Suppose what I'm trying to say here is, okay, suppose you have a beam like this, okay, and you have suppose a pin joint here, some roller here, and suppose that you have some point loading here, some point loading here. Okay, this type of question is there. Okay, now drawing bending moment diagram seems to be a little hectic. Okay, so there is an easy way to draw the bending moment diagram of these types of beam. Okay, suppose I am drawing the bending moment diagram. What I will do is, okay, I will simply, suppose I want to fix this support, I will fix this support. Okay, I will fix this support, and now what will I do, you will have some reaction here. Okay, so you have one, suppose this is force number 1, this is force number 2, and this is force number 3. Now simply draw the bending moment diagram of these forces, assuming that this support is fixed. Okay, suppose you are drawing for one force. Okay, remove all the other forces, assume that your beam is fixed like this, and you are having a load like this. Suppose it is R1. Okay, draw the bending moment diagram. I think you know how to draw the bending moment diagram of this type of question. It is simply, what it will be like, it will be simply a straight line, isn't it? It will simply be a straight line. It will start from 0 here, okay, and it will go something like this, okay, all the way up to the support, and this is your positive. This is for R1 alone. Okay, now suppose you have another force, R2 is there. Okay, let it be R2. Okay, now remove all the other forces, assume this joint to be fixed. Okay, apply R2 and draw the bending moment diagram. Okay, I think you know how the bending moment diagram will look like. It will look something like this. It will look something like this. Are you able to understand the sign? Okay, if you are not able to understand the sign, you cut at any section. Suppose I am cutting at this section. Okay, this is your R1, so I think the resisting moment will come like this. It is anti-clockwise on the left section, so it is positive. Look here, cut at this section. Okay, cut at this section, what will you get? This is your R2, so I think the resisting moment will be clockwise, so I have taken it as negative. Okay, sign you are able to understand. One more force is remaining, your R3 force is remaining. What will the R3 force be look like? Okay, on the right section, you will be having this type, so I think it is negative, isn't it? So it will be something like this, negative. This is due to R3, this is due to R2, and this is due to R1. This is your final M by EI diagram. You can use this diagram and solve just like we were solving before. Okay, just like we were solving before, you solve the question. Okay, so this is how you draw bending moment by parts. Okay, okay, let me just repeat the steps. The step is very simple. You just fix one of the supports. Okay, fix one of the supports. Next step is draw BMD, okay, individually, okay, individually for all forces. Okay, for all the forces present, you draw their bending moment individually and then you can solve. Okay. Theta D. Okay. Suppose I want to solve one question on this. You have a question here. You have to solve by bending moments by parts. Okay. If you think you can draw the bending moment diagram, that is good enough. Okay. If you can. But if you cannot draw it, then use bending moment by parts. It's a very simple technique. Okay. And it is very handy in objectives. Suppose I am giving you one question. Listen carefully because we will solve only one question on this. Okay. You have pin joint here. You have roller here. And you have overhang also. So here you are having 150 kilonewton force. It is located at 4 from here and 6 from here. Okay, this is 4 and this is 6. Again this overhang is of length 4 and another force is acting here. It is 30. Okay, 30. Okay, you have to find deflection at point, say I am naming them, this is your point A. Okay, let this be point B, point C and point D. You have to find deflection of point D. Okay, find deflection of point D. If you look carefully, this question can simply be solved by your standard method itself. Okay, I think I have solved a similar question by standard method. You don't need moment area method for this question. If it comes in objective, you can directly go by standard method. But since we are trying to understand how moment area by parts work, I want to solve this question by moment area. Okay, otherwise it can be solved by directly by your standard method. Now first of all, tell me what is the reactions here. Okay, tell me what is the reaction here. I think this reaction will be 150. Okay, 150 multiplied by 6 divided by 10 from this force. What about this 30? What about this 30? 30 will give you a moment of 120. Okay, so I think you will get minus 120 divided by 10. Is it okay? I think we have done this already. Okay, I don't want to repeat it. 150 into 4 divided by 10 plus you will get 30 directly plus you will get 120 upon 10. Okay, so this one I think you are getting it as 102. Okay, this one is not required. 102 you will get this one, so I am rubbing everything. Okay, this value will come out to be 102. Okay, this one is not required. Now you have to draw M by EI diagram by parts. Okay, once you know this reaction, all you have to draw is your M by EI diagram. So suppose here I am drawing this M by EI diagram. Okay, concept you already know. What you have to do, you have to fix this C support, and draw the bending moment diagram individually for this 102. Forget about this pin joint. Okay, now you have this reaction 102. Okay, so your question is something like this. This is your overhang, this is fixed from here. You have three forces, 150, 102 and 30. Draw the individual bending moment diagram for these forces. Okay, see, I am drawing for 102. Okay, 102 I am drawing. What will it look like? It will start from 0 and suppose here your fixed support is, so it will be linear. Is it okay? This. What will be the value? I think it is 102 into 10, 1020. Is it okay? This is 10. Okay, come back to this 150 force. 150 force is applied somewhere here. Okay, so it will again be linear. It will go like this. Okay, what is this value? 150 into 6, I think it is 900. Okay, and mind you, it is negative and this one is positive. Okay, now come to this 30. Okay, come to this 30. 30 is again negative. 30 into 4 is how much? 120. So you will get this value is 120. Okay, this is again negative. This is your M by EI diagram. So you can divide these values by EI. 900 by EI, 120 by EI. Okay, this looks a slightly bigger, confusing here. Okay, 120 is very small as compared to, so it will be very small value. It is something like this. This is 120 upon EI and this is 900 upon EI. Obviously it is negative. Okay, I hope you are able to understand. This is your M by EI diagram for this beam. If you draw it in the normal method also and you solve everything, you will get the same thing. Okay. Okay. Now you will argue that, sir, this is a roller here and it should be zero moment here. Okay, so it is a zero moment here. You calculate it 1020 and this is 120 and 900. How much will you get? 1020. So they will cancel out and here you will have zero moment. Net moment is zero because it is a roller. It has to be zero. Okay, so you will get the same bending moment diagram. It will look something different because you know these values will cancel out each other. Okay, and you will have different look, but the values will remain the same. Okay, this is a shorter way, very quick way to draw bending moment diagram. You should remember this way. Okay, now what do we have to find out? We want to find out delta D. Okay, this is your beam. Here you have a pin joint, here you have a roller, here you are having some loading, here you are having some loading. If you think about it, how will this deflect? Okay, it will deflect something like this. Okay, this part may actually come down here also. I don't know for now. Okay, for now I cannot say. Now suppose I draw a tangent at this point C. I'm drawing a tangent at this point C. Okay, diagram is not clear, but it is okay. This is tangent at C. Okay. Okay, what is this value? Is it, this is suppose point D, so this is TD with respect to C. I want to find this delta. Okay, what is this? This is theta C. Okay, if I extend this tangent to the back, okay, this point is A. Can you tell me what is this value from here to here? Is it T A with respect to C? Okay, and this length also you know. How much is this length? It is 10 meter. So I can evaluate the value of theta C. Look, this triangle. Okay, this triangle. Theta C is equal to TA by C divided by 10. Okay. Once you know theta C, these are opposite angles, theta C. So this is also theta C. Okay. And this is how much? I think it is 4 meters. Okay. This is 4 meters. So in this small triangle, if you use this small triangle, okay, what will you get? Theta C is equal to this entire length. Suppose I am calling it at XD divided by 4. So your XD will be equal to 4 times of theta C. I want to calculate delta D, this value delta D. Delta D is how much? XD minus TDC. Okay, XD minus TD by C. XD is nothing but 4 times of theta C. So 4 theta C minus TD by C. So to calculate deflection at D, I need theta C. Theta C I have already calculated. TD by C I can calculate from bending moment diagram. I think if you can calculate these values, you can be able to obtain theta delta D. Is it okay? Okay, same approach is there. Whatever we were doing in simply supported, just use your brain, basic trigonometry and your brain. That is it. Okay. I think you will be able to solve this. Think about it. Now I need theta. Sorry, before that I need theta C, right? Theta C is equal to how much? It is TA by C divided by 10. TA upon C divided by 10. For this I need TA upon C. T upon C is nothing. Look at your bending moment diagram. This is your point A, this is point B, point C and point D. Okay, TA upon C is nothing but this total area, okay, multiplied with CG, distance from point A. Okay, CG distance from point A. I think you will be able to solve this. Okay, very simple. Okay, because your bending moment diagram is something like this. I am drawing here again because you have to go back. Something like this and this. Okay, so TA by C, A point is here, C point is here. TA by C means area multiplied by distance from point C, okay, of its CG. So suppose I'm talking about this triangle, red triangle, and the CG will be somewhere here. Okay, it is at a distance of how much? 10 upon 3, because this is 0, this is 10, and this value is how much? 1020 upon EI. So can you tell me what is the area multiplied by distance from CG of this red triangle? It is half 10 1020 upon EI. This is the area, half base into height, multiplied with 10 upon 3. Okay, multiplied with 10 upon 3 because of the moment of area. Okay, plus let's talk about this small triangle. This is small triangle. Okay, what is the area? Half. This distance is how much? I think it is 6. Okay, so this is your 4, so this will be 6. So half 6 into this value is how much? I think it is 900 upon EI. So this is half 6 900 upon EI multiplied with distance from CG. This value is how much? 6 by 3, 2 meters. So this is your TA by C. You solve it. Okay, you solve it. I think this value will come out to be 12400 by EI, TA upon C. Okay, there may be a calculation mistake. If there is one calculation mistake, solve it on your own. Okay, 12400 upon EI divided by 10, so it is 1240 upon EI. Theta value is 1240 upon EI. I think one of these things we have calculated. Theta C is there. Now we want TD upon C. TD upon C. What is TD upon C? Again, you look at your moment diagram. Okay, your moment diagram is something like this. Okay, this is 12 upon EI, this is 900 upon EI. Okay, and this is also there negative. This is 120 upon EI. This is 0, 4, 10 and 14. Now TD upon CI. This point is A, B, C and D. Okay. So what all you have to do is this red area multiplied with distance of CG. So what is the area? It is half 4. Okay, 120 upon EI. This is the area multiplied with distance. Distance is how much? 1/3 of 4. So it is 4 by 3. I think this is your TD upon C. It will come out to be nothing but 640 upon EI. Is it okay? 640 upon EI. Now, okay, it is better that you use sine. Okay, if you don't use sine, you will make a mistake here, just like I have made a mistake here. Okay, this area was positive. Okay, this area was positive, so you have a plus here, but this area is negative. Okay, this area is negative. Be careful. This area was below, so this is negative, so use minus sign here. Okay, don't make this mistake. Use minus sign here. This also will come out to be negative because this is below this axis. It is a negative area, so you will have minus 640 upon EI. Now use your equation. Okay, now use your equation. You will have delta D is equal to 3 theta C minus T. I think C by D is there. Okay, C upon D, or rather D upon C is there. Is it D upon C? Then we have made a mistake here. Okay, we have made a mistake here. If it is D upon C, CG distance will be measured from D. It will be 8 by 3. Okay, answer will remain the same. Now, final step is delta D is 3 theta C. Is it 3 theta C? 4 theta C. Okay, this is 4 theta C minus whatever we have derived earlier, this equation, 4 theta C minus TD by C. You have all the values here. Put the values 4 into theta C is how much? 1240 upon EI. 1240 upon EI minus 640 upon EI. Okay, this will be your delta D. Okay. So I think you can solve this and get the value. Okay, I don't have the value with me. You can solve this and get the value of delta D. That is what was asked in question. Okay, so this is how you solve moment area by parts. Okay, I am showing you one more question. I am not solving it because it takes a lot of time to solve a question. Okay, I don't have that much time, so I am just showing you how to do it. Suppose you have this type of question. Okay, you have some UDL like this. Okay, now it is very difficult to draw the bending moment diagram of this type of beam directly, but if you use moment area by parts, it is very simple. Look here. Okay, you will have some reaction here and some reaction here. What you do, you forget about this support and you fix it. Okay, you fix this support. Okay. Now draw the bending moment diagram for this force R1. I am drawing. R1 will look like something like this. Is it okay? This is the bending moment or M by EI diagram due to R1. Similarly, you can draw M by EI diagram due to this UDL. It will look something like this. It will be parabolic and it will look something like this. Okay. So this is how you can very simply draw the bending moment diagram of any beam if you use moment area by parts. Okay. The step is simple. Just fix one of the supports and draw the bending moment diagram due to all the other supports, all the other forces. Okay. That is it. That is all you have to do. Okay, so I think moment area you must have understood. For practice you can solve more questions if you like. Okay. Next method that we are having with us is conjugate beam method.